Welcome to Module 54 in this series of lectures on statistical process improvement and statistical quality assurance. We're in this module going to discuss data analysis for smaller than half fractions of 2 to the p studies, quarter fractions, eighth fractions, 16th fractions, and so on. The basic notion, the basic ideas used are the same as those for half fractions. In fact, what one does is to, for computation purposes, initially ignore the last few factors. So if I'm talking about a quarter fraction, I ignore the last two factors. If I'm talking about an eighth fraction, I ignore the last three factors, and treat the data as if they were a full factorial in the first factors. Use the Yates algorithm, judge the significance and the practical importance of what comes out of the Yates algorithm, and only then, after that is done, interpret the results in light of the alias structure. At that point, recognize that, oh no, there's not just the initial factors, but there are all p of them to take into account. Where there is some replication, then one can use confidence limits, basically find margins of error for the output of for the values output by the Yates algorithm. Where there is no replication, then all that one can do is to do normal plotting. To be absolutely explicit, if this is a quantity in the last column of the Yates algorithm, the margin of error that one attaches to it is this: a t-value times a pooled s times a 1 over 2 to an appropriate power, and the appropriate power is this p minus q, the number of factors p minus 1 if it's a half fraction, minus 2 if it's a quarter fraction, 3 if it's an eighth fraction, and so on, and then the square root of the sum of the reciprocal sample sizes. The pooled S is derived from pooling sample variances in the standard way, and degrees of freedom are total number of observations divided by our total number of observations minus the number of samples, number of groups, which is 2 to the p minus q. So to return to this Hansen and Best catalyst study, that's an example where there are 5 factors and only 8 different conditions were combinations of conditions were studied. So the p minus q is 3, and one begins by ignoring the last 2, that is q equal to 2 factors. So one makes use of a 3-cycle Yates algorithm, and here is how things get set up to do that. If you will look carefully at these combinations that are listed in this first column and ignore factors D and E, whether they are there or not there, you should see that the combinations there have been listed in Yates standard order as regards factors A, B, and C. One then puts the Y bars in that same order, and then after 3 columns of the Yates additions and subtractions and division by 8, which is 1 over 2 to the 5 minus 2, 1 over 2 to the 1 over 2 to the 3, that is 2 to the 5 minus 2, one gets these estimates. And the question is, what are those estimates of? Well, if there were no final two factors, this would stand for the grand mean, this 24.048. But recognizing that there is aliasing, that there's confounding going on, that must be the grand mean plus aliases. If there were no factors D and E, on this row would sit an A main effect, but recognizing the existence of these last two factors, that has to be A main effect plus aliases, and so on. This third row, if there were only three factors, that minus 0.129 would be the B main effect. Well, it's not just the B main effect, it's B main effect plus all alias with it, and so on. The original data had three sample sizes that were larger than one. If one pools the three sample variances from those three samples, one of the sample sizes was 3, one was 2, and another one was 2. One gets a pooled S squared of 1.872 that has a square root that is 1.368. If one then recognizes that sample size 3 and two samples of size 2 gives one 4 associated degrees of freedom, here's a t-value for 4 degrees of freedom. There's a pooled S. Here is 1 over 2 cubed, and here is a sum of reciprocal sample sizes. That is a margin of error to associate with anything in this column of estimates here is 1.195. If one looks carefully at this list, there are 1, 2, 3, 4 entries in that table. We're not going to pay attention to the grand mean plus aliases, but there are 4 of the 7 of those other estimates of sums of effects that are bigger than their margin of error. So if one then collects them into a table, there are the 4 values that I identified on that other slide, and that 5.815 that is right here, that is A plus A main effect plus aliases. Well, what's aliased with the A main effect? It is the BCD 3-factor interaction, the ABDE 4-factor interaction, and the DE 2-factor interaction. Where does that come from? That comes from looking at the alias structure that corresponds to the way the two generators that were used in designing this experiment. So if you look back at what I'm saying at the previous module, in this business of multiplying letters according to these special rules of multiplication, starting from the two generators that were used to pick out the combinations of the 5 factors used in this quarter fraction study, you get these 4 sums that are being estimated by those numbers in the estimate column. the first thing to notice here is 3 of these are bigger than the other one. So even though this is statistically detectable, it's probably sufficient in this example to concentrate on the biggest 3. That doesn't leave us, however, with an absolutely clear interpretation of this experiment for the following reason. There are at least 4 plausible interpretations of these 3 guys being big. The simplest is that there's an A main effect, there's an E main effect, and there's a D main effect, and everything else is small, is negligible. On the other hand, you could argue that, well, no, that's not the simplest interpretation. Maybe it's A, E, and the AE two-factor interaction, and maybe it would be simpler to think of factors A and E as being the only thing that's driving this system, them operating with an interaction, but there's no factor D involved. Well, that doesn't exhaust the possibilities. I've just pointed out the meaning of this and the meaning of that, but you could also look at A, D, and AD by saying A, D down here, and AD up here. And that also doesn't exhaust the possibilities. There's also, sticking to those first 3 rows there's also an interpretation that says that D and E and those 2 factors interaction are the big actors, or the most important elements of those sums. What this begins to say to you is the smaller the fraction, that is, the larger the Q, the larger the inevitable ambiguity of interpretation of these results are going to be. You start to talk about a 1/8 fraction, a 16th fraction, and so on. You're likely, in order to disentangle everything, going to need some follow-up study. Really small fractions are most useful as screening studies to pick out a few likely candidates from a large list of many potentially important factors that are going to subsequently be studied more in depth. In fact, in this particular example, a follow-up study confirmed that D really was an important variable in this study, and ultimately the interpretation of 3 main effects as being a good description of this system was confirmed as being most helpful from an engineering and practical point of view. It's also the case that by looking at signs for A, E, and D, so going back here, A, E, and D, well, I've got to be careful. So E is aliased with BC 2-factor interaction, and D is aliased with ABC 3-factor interaction. So I should be looking on this line and this line, looking at those signs. If I want large response, I want positive signs, and what one then wants is high A, low E, and high D for the for the biggest fitted or predicted response.